Hey everyone, in this video we're going to discuss section 4.2a, which is about polynomial functions of higher degree. This video hopefully is going to remind you of some key features you learned about last year in Algebra 2 regarding polynomials, and it's going to provide us a good foundation for our work moving forward as we do more things with polynomials. So first, just as a reminder with standard form arranges our terms in order from the highest exponent to the lowest exponent. Okay, so that term that's first is our leading term. A sub n stands for the leading coefficient. Okay, and then we would say that this function has a degree of n because n would be our highest exponent. Okay, and then all of the other terms that go after that have the next highest exponent, and then the next one, all the way until we get our constant term at the end. So the reason that this is important is that leading term is going to dictate the end behavior of our polynomial. So we need to take a look at what the degree of the polynomial is, or that highest exponent, and then we also need to take a look at the leading coefficient. Okay, so it's important to us to know what the graph is doing long-term on the left and on the right. So for this, I like to think of some model functions that are going to kind of help represent all functions. Okay, so the first one, for an odd function, we're going to think of x or x cubed. Okay, both are odd, and I can tell here that that's true because our degree is an odd number. And then for even, I like to think of x squared. Okay, so we have those two different types of degrees, okay, or those exponents. And so the first one is if we have a positive leading coefficient, if a sub n is greater than 0. Well, if I think about what x looks like the function, okay, I know it looks like this, and then even x cubed looks like this. So if I'm taking a look at the at my end behavior, I see that on both of those, as I'm looking to the left, I'm going to negative infinity. Okay, so I'm pointing downwards. And as I'm looking to the right, I'm pointing upwards. I'm going to positive infinity. Okay, so all odd polynomial functions will have this type of end behavior with a positive leading coefficient. Now, if we have a negative leading coefficient, it switches it. So we're going to rise to the left, and then we're going to fall on the right. Okay, for x squared, or an even function, okay, I know that looks like a parabola. Okay, I know that when the leading coefficient is positive, both sides point up, and when that leading coefficient is negative, we point down. Okay, so the important thing that we need to know about when we describe end behavior in this class is we're going to talk about it in terms of limit notation. So looking at that first example, for instance, we have f of x is equal to 3x to the 5th minus 4x cubed plus 7. So our leading term, looking at it, it might be written in standard format, it might not be. Okay, our leading term is this one because that's the highest exponent. Okay, so I see here that we have a positive leading coefficient, and then I also see that I have an odd function. So I know that even though there's a lot of other terms, it might have some twists and turns to it, I know that my end behavior is going to look like this. Okay, so when we write this in limit notation, as a reminder, this looks like the limit, and then underneath the lim, I'm going to put x as it approaches. Okay, so the first one we're going to look at is going to negative infinity. That's going to be the left side. You don't need to write left, but that's the left side. Okay, we need to put the function we're talking about, so the function of f of x, and then we know that on the left-hand side, we're approaching negative infinity. We're pointing down. Okay, then on the other side, okay, we're going to look at the right side, the limit as x approaches positive infinity of the function f of x, and that points up, so it goes to positive infinity. So hopefully that limit notation looks familiar to you. I'll have you go ahead and try B and C, pause the video, and then when you're ready, unpause, and we'll just double check what you have before we move on. Okay. Welcome back. Hopefully that was enough time and you paused. Looking at b for our function g of x, it was not written in standard form, so that leading term was actually the negative x to the 4th one. Since we have a negative leading coefficient and we had an even function, I knew that they both were going to point down. So the limit as x approaches negative infinity, our function was g of x, was equal to negative infinity, and then the limit as x approaches positive infinity of g of x was also equal to negative infinity. For c, h of x's leading term was negative 12x cubed, so I had a negative leading coefficient, and I had an odd function, so I knew that to the left we were going to rise, and then to the right we were going to fall. So the limit as x approaches negative infinity of h of x was going to be equal to positive infinity because it points up. And the limit as x approaches positive infinity of h of x is equal to negative infinity. It points down. All right, okay, so flipping over your page, we have an important theorem about local extrema and then zeros of polynomial functions. So we have our end behavior, but now let's start talking about our zeros. So first of all, as a reminder, the word zero refers to an x-intercept. Okay, so a polynomial function of degree n will have at most n minus 1 local extrema, and then it has at most n zeros. Okay, so let's say, for instance, that I was talking about, let's talk about the function x cubed. Okay, so I know that the cubic graph looks something like this. Okay, so first, the first part is saying the degree n has at most n minus 1 local extrema. So at most, any sort of cubic function can have at most 2 extreme points. Now, the parent function doesn't have any, right? Because there's no local maxes, local mins. But we know that cubic functions can have some peaks and valleys to them if we add on other terms to it. So a cubic function could also look like this, okay? Where I see that I have a local max and I have a local min. So at most, because the degree was 3, I can have 2. Okay, if your degree was going to be 5, you can have 4. If you have a degree of, 17, you can have at most 16 mins and maxes, okay? But you're not guaranteed to have them. Okay, and then the second part says that it has at most n zeros. So again, since our degree was 3, we can have at most 3 x-intercepts. Now, again, we know with the parent function, we only had 1, but if I look at the other graph that I have 1, 2, 3 x-intercepts. So the important part of this is that if we know what the degree is, we can kind of plan out like long-term, like what this could look like, okay? We know how many maxes and mins we should have. If we have more, we know we've done something wrong. Same thing with the zeros, okay? So when we're looking at the zeros, sometimes we have our function written in standard form, but we also can have it written in factored form. So as a reminder, factored form, and I'm just going to put a little example on here, could be like f of x is equal to x minus 1, and maybe it has an exponent of 2, x plus 1, and x minus 4 cubed. Okay, so the multiplicity is talking to us about what the exponent is on one of the factors, okay? So I would say here that this has a multiplicity of 2, this factor has a multiplicity of 1, and this factor has a multiplicity of 3. So the multiplicity is important to us because it's going to tell us the behavior of the function at the 0 or the x-intercept, okay? So if we have an even multiplicity, so for instance, in my last example, I had an x minus 1 squared term. That tells me that at that point, at x equals 1, I'm going to bounce off the x-axis, okay? I'm not going to actually cross it. I'm just going to bounce and keep going in the same direction, okay? If I have an odd multiplicity, so in my last example, let's say x minus 4, for instance, x minus 4 cubed, okay? What that would tell me is that at 4, we're going to cross, and then we're going to keep going onto the other side. So looking at those factor and those multiplicities, it tells us, okay, well, what happens at those zeros? So in example 2, we're going to determine the end behavior, the zeros, and the y-intercept of the polynomials. And then for each zero, we're going to state its multiplicity. So we're just starting to find this stuff, okay? We're collecting the information. So first, let's talk end behavior. Okay, so end behavior, we are going to write that anytime it says to determine the end behavior, that it does mean, even if it doesn't state it, to write it in limit notation. Okay, but let's collect some facts about it. So first, finding my leading term. My leading term is going to be 4x cubed. I see I have a positive leading coefficient, and this is an odd function. Okay, so I know that we're going to fall on the left, and we're going to rise on the right. So writing my limit notation, I'm going to have the limit as the x approaches negative infinity. Let's do the left-hand side first, of f of x is equal to negative infinity. And then for the right-hand side, I'm going to have the limit as x approaches positive infinity of f of x equal to infinity. Okay, the next part told us that we were going to find our zeros. Okay, so we're going to figure out where our x-intercepts are. Okay, well, it's easy to do that when we have this in factored form. I see that it's written in standard form, so if possible, we're going to try to factor it. Now, I'll give you a spoiler alert. A lot of this unit, or at least a big part of it, is going to be how do I factor something that we haven't really been able to factor before. We're going to learn some new skills, but for right now, let's use those Algebra 2 skills that you know. So for instance, it's not a quadratic, okay, so I can't just factor it like we're comfortable with. However, I do see that each of these terms has an x, so let's go ahead and factor out an x. So I'm left with 4x squared minus 19x minus 5, and I do see what I have left over inside is a quadratic, so let's see if we can factor that. Spoiler alert, we can. Okay, so that's going to leave me with x plus 4 as a factor, and then x minus 5 as a factor. So hopefully you got something similar. If I messed up, please let me know so that way I can make a note to let everyone else know that I made a mistake. But okay, so when I'm looking at this in factored form, this is going to tell us what our zeros are. So as a reminder to find our zeros, to find our x-intercepts, I would set each of these equal to 0 and then solve for x. Okay, because those are going to be the numbers that would make the whole polynomial be equal to 0, hence the name 0. Okay, so the first one is going to be x equals 0, and the directions did say to state its multiplicity. So for that, we're looking to see on those factors, were there any sort of exponents on them? And in this case, I don't think there was. We just factored that there was only one factor of each of those, so its multiplicity is 1. And I'm just going to represent that with an m1 after it. Okay, I'm going to have x equals negative 1/4 with multiplicity 1, and then x equals 5 with a multiplicity of 1. Okay, and then last but not least, the y-intercept. As a reminder, with the y-intercept, that's going to be our value of y when x is 0. So we're going to plug in 0 for our function and see what our output is. Okay, well, in this case, looking pretty good here because each of these functions has an x in it. If I plug in 0, it just zeroes out the whole function. So our y-intercept is 0, 0. Okay, the next example, I have one as well. G of x is equal to negative 2 times x minus 3 squared times x plus 5 raised to the 6th power. So go ahead, pause the video. I'm going to have you try this one out yourself, see what you can remember, see how you can do. When you're ready, go ahead and unpause and we'll go over it together. Are you paused? Okay, if not, let's go ahead and let's check over it. Here we go. Okay, so our end behavior, our leading coefficient was negative, and we had an even degree, so we should be pointing down on the left and the right. That gives our limit statements for both negative infinity and positive infinity equal to negative infinity. One thing just to make sure of, our function is called g of x. Make sure that you have a g of x written here, because that is the function we're referring to. Okay, this was already given to us in factored form, so that made it very easy to find our zeros. Okay, so first we had x minus 3 squared. When I set that equal to 0, that multiplicity doesn't truly matter because I know that I would just square root this anyways. Square root of 0 is just 0, so x minus 3 would be equal to 0. So that gives us a 0 of 3. Okay, it has a multiplicity of 2, which means that it would bounce there. And then for x minus 5 as a 0, it has a multiplicity of 6, which also means that it bounces. Perfect. That bounce was just a little extra. Okay, but that's what would happen at those. Okay, and then for our y-intercept, when we go to plug in 0, okay, I got a pretty small one, you could say. I got a y-intercept of 0, negative 281,250. If you got something different, let me know. But that seemed right to me. All right. Do we want to graph it? Just kidding. Well, that's what we're going to do next. Let's go ahead and turn our page. Okay, before we actually get to graphing though, one thing that we also want to have a skill of being able to do is to write an equation for a polynomial in factored form and in standard form. Okay, so if you're given a graph, you should be able to figure out what its equation is. So I think writing it in factored form is easiest first, and then we can go ahead and we can write it in standard form. So for this function, it doesn't tell us what to name it, but let's call it f of x. Okay, so I know that for f of x, first if I write it in factored form, I'm looking at where my x-intercepts are because those are going to be where my zeros are at. That's going to help me build my factors. So for instance, I have a 0 at x equals -3, so that means that its corresponding factor would be x plus 3. Okay, same thing here. I have a 0 of 1, which means its corresponding factor would be x minus 1. Okay, so we're feeling good. We have an x plus 3 factor. We have an x minus 1 factor. Now, I do see that we have it crosses and it bounces there. Okay, so that means that we are going to have some multiplicity. So at x equals -3, I know that I cross, so that means that it needs to have some sort of odd multiplicity. And at x equals 1, I bounce. Okay, so this has to have some sort of even multiplicity. Okay, that also should make sense to me because I'm going to have an odd number plus an even number. I'm going to want to make sure, and that would make sure that we have our end behavior going in different directions, okay? So I don't know if this is a cubic. I don't know if it's a quintic polynomial. I'm just going to choose one because that's going to dictate what something else is a little bit later on. So maybe we say this is a cubic. Okay, I'm going to make x plus 3 have a multiplicity of 1, and then x minus 1 have a multiplicity of 2. Okay, so you might be thinking, great, we've done it. Moving on. Not quite though, okay, because we know that there could be some sort of leading coefficient. And in fact, I do know that I'm going to need to have a leading coefficient that's not 1, because look at our end behavior. We rise on the left and we fall on the right, and a normal cubic function does the opposite. Okay, so I do know that my leading coefficient does need to be a negative number. We're just not really sure what negative number that is yet. Okay, so I'm going to put an a in its place for right now. Okay, so what we're going to need to do is we're going to need to solve for what a is. And to do that, we need to find some sort of other point that's on this function to plug in, and then we can solve for it. Okay, just like when we were doing this with writing a quadratic function in vertex form, okay? So let's find some sort of nice point on here. I'm looking at 2, -1. That seems to be reasonably nice, so let's go ahead and plug that in. So my output is -1. A is what we're solving for, and then 2 is my x value, so I'm going to have 2 plus 3 raised to the first power, and then 2 minus 1 squared. All right. Okay, so let's see, this is going to be 5 times 2 minus 1 is 1, 1 squared is 1. So going ahead and dividing by 5, it looks like a is equal to -1/5. So our function in factored form is equal to -1/5 times x plus 3 times x minus 1 squared. All right. Okay. It also says that we want to write it in standard form. So really what all that means is that we need to multiply this all out and get it so it's not in factored form, and we arrange our exponents as needed. So I'll let you go ahead and find the standard form, and we'll check this over in class. Okay. Last ones that we're looking at, example 4. For both A and B, what we're going to do is we're going to sketch graphs of polynomials without using a calculator. Okay, so what that means is we need to collect all of our information about it and then be able to go through and sketch it. The big things that we want to know is we want to know what the zeros are. Okay, we want to know what the y-intercept is, and we want to know what the end behavior is. Okay, those are the 3 big things that we need in order to be able to sketch a reasonable graph. It doesn't need to be perfect. We might not have all of the y values super consistent, but that gives us a basic shape, and that's ultimately what we need. So I am going to ask you one more time to go ahead and pause the video. Try out part A and part B yourself. When you're ready, we're going to unpause and we'll go over this together. I know I've asked you to try a lot, but it's good for you. Okay, practice is good. All right, hopefully you've had a chance to go over that. Let's check over these final 2. Okay, so looking at example 4, there should have been 4 zeros. X equals 0 was 1. It's easy sometimes to forget that x out in front, so that is 1. Okay, we have x equals -1, x equals -5, and then x equals 2. For x equals 0, -1, and -5, since they've all had an odd multiplicity, 1, 1, and 3, that means we're going to cross, and then x minus 2 has an even multiplicity, so we're going to bounce there, okay? The y-intercept, when we plug in 0, is going to be 0. And then the end behavior, our leading coefficient, looking at all of these, they all had a coefficient of 1. I didn't have any other sort of value out in front, so that leading coefficient was 1. And then the degree is 7, because if I go ahead and add up all of what my exponents were, I have 1 plus 1 is 2, 2 plus 3 is 5, 5 plus 2 is 7. So my end behavior was going to fall on the left and then rise on the right. So here's what my graph looks like. Okay, one question that gets asked a lot is, how do we know how high to make our peaks and how low to make our valleys? One thing that you can do if you would like to is to pick a point. Let's say, for instance, that I look at 1. I can plug that into my function to figure out what that y value is. But again, we're just trying to get a specific shape, okay? And actually, this sets up nicely what we're going to do in calculus a little bit later, maybe a year from now. We'll be able to have a more concrete way of finding how low our lows are and how high our highs are, okay? Okay, last but not least for B, it was given to you ultimately in standard form, x to the 4th minus 13x squared plus 36. We weren't able to factor out an x from it. However, sorry guys, however, if this is something that I can factor, okay? So my factors would be x squared minus 4 and x squared minus 9, two difference of squares. So factoring all together, I get x plus 2, x minus 2, x plus 3, x minus 3. So that gives us our 4 zeros, and since all of them have a multiplicity of 1, we're going to cross through all of them. Okay, our y-intercept is 36, and that was pretty easy just to pick off because that was our constant over here. And our end behavior, since our leading coefficient was 1 and we had a degree of 4, which was even, I know we're going to rise to the left and to the right. So on our graph here, the only thing that was slightly different than the other one, not necessarily slightly different, but stands out a little bit more, is the y-intercept. So again, 36 is kind of high. I'm not going to spend my time making, 36 little dashes. So it's okay just to put a 36 there and to label it, so that way we know that's representing 36. These ones are going to represent, 1, 2, 3. Again, we're just trying to get an ultimate picture of what this looks like, and it doesn't have to be 100% perfect. So that's all I have for this video. Hopefully a lot of this was reviewed to you, and then moving forward, we're going to start adding in some other key details that are going to give us maybe a better picture of what a polynomial could look like. So that is all for this video, and I will see you all later.